The third speaker for this session is Richard Eisenberg, who will be telling us about a non-allocating option.
Is this picking me up? Yes, good. OK. Hi, everyone. Thanks for coming to this talk. So this is about, this talk is about, well, our old friend option. And so here we have this nice option type, which is really a wonderful thing, right? Because it means that using option, we can have better error tracking, right? If a function returns an option, we know it might fail in some way, and then it might return none. It forces us to check this result. All very nice things. Let's look at an application of it. So here we have a square root function, but of course negative numbers don't have square roots that can be represented in float. So we check if the float is less than 0, then we just want to return none. Otherwise, we want to return the actual result wrapped up in a sum. But at runtime, what this is going to do is we're going to have this box on the right that contains our actual answer. But then there's this other box in the center, right? And this represents the sum constructor. And we don't really want that box. We just sort of want to say, oh, well, it didn't fail, so here's the answer, right? And this extra box, this causes an extra allocation, and sometimes we want to eliminate that. In many applications that we have, both in Jane Street and outside of Jane Street, I'm sure, it doesn't matter if we sort of allocate a little bit extra. The function that calls safe square root is going to pretty quickly pattern match on this and eliminate it. But sometimes we have a couple of applications, at least within Jane Street, where every allocation matters. And we do want to make sure that we don't have any of them. And so this kind of paradigm or a model isn't available to us. So we're unhappy about this box. What can we do about it? So we want to avoid this allocation. So the idea behind all of this is not a new idea. Aspects of this approach will be new, but this first idea is not new. We want to store some x just like x, right? Instead of doing this extra step, let's go instead of this just to this. OK. The immediate problem that we run into is, well, we still have to tell the difference between some and none. And so to do that, we're going to have to come up with some representation of none that's distinct from every other value that's out there, right? Because we don't know what the sum is going to wrap. So if we're going to have a none that's distinct from it, then it has to also be distinct from every other value out there. Well, here's an idea. Let's just use null. Well, what do I mean by that? So here I'm using null to represent the bit pattern that's just all zeros. In contrast, other values, we can have a pointer. Well, a pointer isn't going to be all zeros because it's going to be a pointer to some valid memory address. So that's not null. Or we might have a tagged int. But a tagged int, well, it's tagged. So the bottom bit is 1. So even the int that represents 0 still ends in a 1 bit. So it's also not null. So that means that null here really is distinct from all other values that currently exist in OCaml. We still have yet another challenge. And that is that we need to tell the difference between none and some none, right? Because I was saying earlier that sum of x is going to have the same representation as x. So that means that if none is represented by null, then some none, well, according to that logic, also has to be represented by null. And this looks like a problem. And so there's a bunch of different ideas that we could attack in this space. The particular idea that we're choosing here is to disallow alpha option option. But of course, we can't do that because option has been around for a long time. This would be backward incompatible, so we're not going to do that. Instead, we're going to create a new type we're calling or null. And we're going to disallow alpha or null. So actually, in the end, we're not going to, and it's going to have its own constructors, null and this. So we can return, this square root of something. So actually, as much as I've been phrasing this as an improvement on option, it's not really. We're going to keep option exactly the way that it's been. There's going to be no changes there that we're looking at. Instead, we're looking at creating a new type or null that has this that's more efficient, but it lacks the ability to nest. So it's not strictly better or strictly worse, but it's just a little bit different, yet we're expecting it to be quite widely applicable. But I said here that I want to disallow alpha or null or null. The way that I'm going to do that is by separating out with-null types from no-null types. So the idea here is that we're going to take all of the types that exist in the world, and well, all of them today are no-null types because all of the types that exist today don't have a null in them. But this new or null type is going to be a with-null type. And those of you who know about at immediate, this is kind of the way at immediate works, in that we distinguish some types as having an immediate representation. If you don't know about at immediate, that's fine. You don't need to understand this talk. But if you do know about it, we're sort of connecting into the same kind of logic here. Okay, so let me sort of demonstrate all of this a little bit in our implementation. So we can go out from here and over to Emacs, and this is showing up. Is this big enough? Can I have someone in the back nod? Yes, good. Okay, thank you. As you can see here, we have an implementation. The implementation that I have here is all of the type system features. The runtime stuff is still a little bit in progress, and I want to give credit to my colleague Diana Kalinichenko, who's done all of this implementation work. And much of the design. I sort of started it, and then she found a whole bunch of problems with it, and it's been refined a bunch. I shouldn't even say that. This was a collaborative effort among a bunch of people, and anyway, as with everything at Jane Street. So we have type T1 here, and this works just fine. Let me prove this to you. I can compile this file, and it compiles without error. So we'll see there's other examples in here, but everything that we see that's not commented actually does work. So we have string or null, and then of course we can have representatives of this type. This :T1 annotation is not necessary. I'm just doing it there for emphasis, right? It's just an ordinary. Whoops, didn't want that. It's just an ordinary type. Okay. Not only for pointery things like strings, but it also works for inty things like int. Let's see what's coming up next. Okay, so we might want to put these things in a list. Well, it turns out that the built-in list, sort of the way that it's defined out of the box, is going to accept only no-null types. So I have to redefine it here to be with-null types. What we're going to eventually do, we haven't done this in our implementation yet, but it actually just go in and change list to accept the with-null types. So users won't have to do this. This is sort of a little fragment because we're still building this as we go. But with this redefinition, we can now say that that list can contain with-null types, so string or null list works. But we don't want to be able to say string or null or null. And so indeed, if I uncomment this, whoops, that's going to fail because that's broken. Sorry, that's just like the command line was, oh, what's gone on here? Something's bad has happened. Okay, there we go. Okay, I don't know what I did wrong there, but I fixed it. So we can see this. Oops, that's not what I meant to show. There we go. So we can see here that we get an error message saying that the kind of string or null is value or null. That's one of these. That means that that string or null is a with null type, but it must be a subkind of value, and value is the no-null types. This is the types of everything since the birth of OCaml. And so it's saying that there's a sort of this kind error here. And that's exactly the kind of error that we want. This string or null really should be prevented. So let me re-comment that and then continue. Okay, so now we get to see some of the challenges that arise around type inference in these things. We're going to need a little bit more space. Okay, so here I have S1, very basic module type. And one question is, when I make an abstract type T like this, is that a with-null type or is that a no-null type? And this is sort of a hard decision to make from a language design point of view. We have decided to make this a no-null type because we think that will turn out to be more convenient. One consequence of this is that this module M1 is going to be rejected because it instantiates T with a with-null type. So indeed, if I uncomment this, and then go down here, and then hit some buttons, then I get an error. And let's see, type T equals string or null is not included in type T because they have different kinds. Okay, so that's what we would expect if plain type T is required to be a no-null type. On the flip side, we can define F1 down here, right? So here I can take the x.t and put it in an or null, right? If I made the other choice around what the meaning of abstract type T was, then F1 would fail instead of M1. And we think that in general, we're going to have more trouble if we allow M1 and disallow F1 than the other way around, right? Because in an OCaml program, there's many, many, many abstract types, right? And we want to just be able to put them in or null. There are not quite so many collections, as we'll see a little bit further down in the file. So let's go on to more examples here. Whoops, gone too far. So now here I have S2, which has this annotation that says that this abstract type T is a with-null type. So that allows M2 now. I can say that I can have type T be instantiated with string or null because I declared that T would be a with-null type. And by the way, types that don't have null, like string, we can still use them in type T. It sort of doesn't use the full space that's available, but that's fine. We don't have to use the full space that's available. But we can't do module F2, right? I said that x.t in this case is a with null type, so I can't pack that in another or null. And so again, this echoes some of the situation with at immediate, that we get certain capabilities, but then we lose other things, right? It's a trade-off. Okay, that's the end of the demo. Let me go back to slides. Okay, so one challenge here was sort of figuring all of that stuff out. There are further challenges around type inference, but there's not quite enough time in this talk to go through them all. But if you ask me after the talk, I'm happy to explain it to you. So another challenge that I do want to spend a few minutes on is around flat float arrays. So the flat float array optimization in OCaml means that if we want to create an array of floats, we use a different representation than all of the other arrays out there. And so when we're allocating an array, we have to decide before allocating the array whether it's going to be a float array or not. And we have to do this in a polymorphic context, potentially. So I'm thinking, for example, in the compiled version of the init function, right, which creates an alpha array, we need to do some work to figure out if alpha is a float or not before allocating the array. So the way that this happens in practice is by figuring out what is the first element of the array, looking at that, and then if it's a float, then we allocate a float array. If it's not a float, then we allocate a non-float array. For that analysis to make any sense, we need this separability property. So the separability property says that, that for a given type, every value is a float or every value is a non-float, which sounds like most types should just sort of have this property, but it turns out not every type has this property. So for example, OCaml allows unboxed existentials, and if you create an unboxed existential that just wraps up the existential variable, you'll get an error saying that this type is not separable because some values are floats and some values are not. So this is actually, every time you make a type declaration in OCaml today, this separability check happens. I should say, it's not clear, everything on this slide is in every OCaml out there. This is not specific to sort of our version or anything we're doing at Jane Street. But float or null is not separable, right? Because float or null has both floats and also null, right? So in practical terms, if we created a float or null array, we might get the first element might be an actual float. Then we'll think, oh, the whole array must be floats. And then when we try to put a null in, well, there's sort of no room for that in the bits, right? All zeros is a valid float. It's just not a valid value in OCaml because floats are boxed and sort of referred to by indirection. So this float or null is not separable. So we have a problem. And it means that we just can't have a float or null array, right? That would be really bad. Well, we have two obvious ways of stopping ourselves from having a float or null array. One is banning float or null, and the other is banning or null array. Well, if we think about this first option, if we try to ban float or null, the way to do that is we could just sort of gratuitously label float as a with-null type, and then that would successfully ban float or null. But that's also going to mean that if we have an abstract collection type, an abstract parameterized type T, it would ban float T. And we think that's going to be pretty painful. So we're not going to do that. Instead, we're right now choosing to ban alpha or null array. And if you want to pack a bunch of or nulls in an array, we can do that with a uniform array or some other collection, right? There's other ways forward, but to use the built-in array that has this flat float array optimization, we're just not going to be able to use it with floats. With or null. So there's actually an alternative solution to this that was floated, I think, 3 decades ago, about just sort of counting the number of sums that precede a none. I could talk more about this. I think this was maybe originally mentioned in a paper by Jacques, but maybe it was coming from somewhere else. But we found a reference from '95 that sort of mentions this alternative idea. But this would mean that the option type is not separable, and that would just be a huge backward compatibility problem. So we can't do that either. So again, I'm happy to sort of tell more details about that. But there might be a way forward. If we didn't have the float array optimization, there might be another route that doesn't involve sort of bifurcating the space of types. Implementation, as you can see, is mostly complete. So we're steaming ahead with this. And sort of once it settles, we'll be looking forward to upstreaming this feature. And that's all I've got. Thanks very much. Happy to take questions.
We've some time for questions.
Okay. Jagari. First, a remark. So this idea, actually, we discussed that with Xavier a long time ago. And I think Xavier even implemented it. It was a slightly different version when you use the fact that no value in the heap has a type that is 2 modulo 4, a value that is 2 modulo 4, so that actually you can have a whole bunch of, so you can represent no and subnon, etc. But actually, this didn't work very well, so we just dropped that approach.
What didn't work very well about it? I mean, so it's incompatible with this float array optimization, but otherwise, that seems good.
I suppose it was not that efficient.
Really? That's surprising.
That means, well, then you have some work when you access. So you have to shift because it can be. So you have more tests to do. I don't know. You have to ask Xavier if he remembers. My other question is that a natural candidate for or-null is optional arguments, but then that means that you cannot use or-nulls as functional arguments. Your thoughts on that?
So that's a good point. I mean, it would be nice to use this for optional arguments. Right now, it seems with the current design that we won't be able to do that because it wouldn't be backward compatible. Because you can have an optional argument that is itself an option. So I guess we could have that be an option, but pack into an or null. It's when we've thought about it, the type inference challenges make us think that we're not going to go in that direction. We might hopefully revisit that, but right now there's not a concrete plan to use this for optional arguments as much as we want to. Yes.
So when talking about performance, you said, well, there's these cases where you have to do where you can't allocate at all and it's useful there. And maybe in other contexts, the allocations are short-lived enough. But I actually just don't believe this story because I think there are lots of contexts where you have long-lived data structures, large data structures that have lots of optionality baked in them. You have some big record with lots of optional fields. Go model a Google protobuf or something. And then we also have internal stuff that looks like this, where there's just a lot of RAM that is dedicated to these extra indirections. And I wonder to what, if we've thought at all about the question of if you took this kind of stuff and applied it to some of the kind of standard things that this community has worked on, like Cook or something like that, whether getting rid of pretty thoroughly getting rid of the non-related indirections would have a performance effect on that kind of code as well.
I mean, I imagine it would. The example at the beginning of the talk would most likely be one of these very short-lived nodes. But of course, we store options in records and in other structures, exactly as you say. Removing them would likely increase performance. We don't have I don't have data to present at this point about that, but absolutely. I mean, we expect once this is available to sort of make a little campaign of trying to change over options into or nulls, and we'll test to see the performance changes there.
All right, thanks for the talk. If you have an or null under an ADT or something that goes under a layer of indirection, is it then safe to call that not null because you won't immediately have this null problem, or do you go all the way down to check for nulls?
I'm not sure I understand the example. Just explain that again.
So if you had something like, I'm not sure exactly how pairs are implemented, but if you had int or null star int or null, would it be safe to call that type not null?
Yes.
Okay.
Because I mean, as long as like what you just described would be a sort of a boxed pair.
Right.
So that's represented by a pointer, which itself can't be null, even though the components can be null. We're in sort of another branch of work, right? We're looking into unboxed types, and we can have an unboxed tuple, and then there's a little bit more complication around how this propagates through unboxed types that we're still trying to work out.
All right. Yeah. Thanks.
Sure.
And let's thank the speaker again.